I feel empty too. Okay, now it's working. Before, I was literally getting issues for some reason where I was just being stuck on one screen. I did 2 backtracking problems. Yo, backtracking is actually so boring. Honestly, if you're studying for your interview, don't do it. I remember one interview, I got a backtracking problem. I was like super sick. I was just trying to find a better way to do it, but then you realize there is no good way, so just do it whatever way you want. Like, just an example, give an array of distinct numbers, return all possible permutations. How would you do this? I guess you'd add 1, you'd add 2, and you'd add 3, so single values, and then you'd update the array with what you've seen, and then you'd pick values from each of these to add to auxiliary arrays, and then you just keep on updating. So you'd add 0 to one array and 1 to another array. Now, the array with 1, it will have a hash set that says, hey, we've already added 1, don't add it again. And then it'll see 0, so add that. Yeah, because they're all distinct integers. I'm not going to do this just because it's easy and kind of a waste. Return all possible subsets. So you start with the empty array, and you recursively add one new value in. Again, we have like a scene array where we show what we've already seen. So you add 1, you add 2, you add 3, and then 1 will say, hey, I've already seen 1. So then I'll add 2 to one instance of the array and 3 to another instance. And then it just keeps on, you add the array every time you see it. But backtracking is kind of not that important. Like, if you know how to do one backtracking problem, you know how to do all of them. Let's do dynamic programming, because dynamic programming is interesting. Return true if you can reach the last index and false otherwise. Okay, let's see this problem. So we know with let's actually just make a false table. False, 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 false. So these are this array will take. Can we reach this index? So initially for index 0, of course we're going to reach index 0, so that's true. But it also has a value of 2, so you can also reach 3 and 4. So then you go to the next value, you can reach 3, but you can also reach this one. Then you go to the next value, you can reach this value because it's true, and you can also reach one more. And then you go to the last value, you can reach that value, but you can also reach one more. Okay, that's pretty easy. I do remember this problem a little bit, but I'm pretty sure that's how you do it, because you just see like, hey, if I can reach 2, then I can reach 3 and 1, and then you check 3 and 1. So if you were doing this with like if you're doing this like without dynamic programming, no dynamic programming, what you would do is you start at index 0, which is 2, or index 0, which is 2, and then you will see, hey, with 2 I can reach, just kind of like a bottom up approach. You can reach what's it, index 1, which is 3, and you can reach index 2, which is 1. Now with index 2, you can reach, you just continue growing this graph, and then it's like a recursive function. As soon as you reach like n-1, you're good. So with index 3, we have 3 branches, so it's not binary, it's like multiple graphs. Multiple paths you take, because that's 3 values you can reach, right? You can reach 2, or you can reach 2 with the value of 1. You can reach index 3 with the value of 1, and you can reach index 1, 2, 3. You can reach index 4 with the value of 4. Now we see this one, and you say, hey, this is n-1. So this is winner, winner, chicken dinner. No gambling though, that's haram. But the idea is, where does the dynamic programming come in? It comes in at this step. So you say, can you reach it with index 2? And if you have that value saved, or yeah, I guess this solution is fine too. Yeah, the solution is perfectly fine. But I guess you're like recalculating, hey, you can reach 3. So you kind of get into like a loop, like, hey, or no, you don't get into a loop. It's like multiple times you're calculating, like, say this index right here, right? Index 2. So you're going to calculate twice, like, hey, I can reach it from this path, or I can reach it from 3 and then go here. So there's like some paths that are duplicated. So that's kind of like the idea of storing it in an array. So you remove those duplications. So if you're at index 0, 1, you can reach 0, 1, 2, 3, 4. Wait, 0, 1, 2, 3, 4. So 0, 1 plus 3 is 4. 1, 2, 3, 4. So that's an equal to. It's fine. And if you ever, a little optimization here is, if you ever get to a block where you can't reach it, then it's obvious, like, you're at a place. Okay, so if you can never, 3, can't reach a block, you can't reach a block after it either. So that's like an obvious statement. So here, return false. And then this for loop, return false. Oh my god, God. Oh, I plus num's I. Okay, let's see what we're doing wrong. Can reach 0 is equal to true. Else for int j is equal to I plus 1. J is listening. j is equal to true. Hey, beats 15%. Everybody's got the same solution. Current is equal to max.max current comma nums I. Oh, same idea. Same idea. But this time, what they do is they store a reference of what's the maximum value you can jump at. So you don't have to update. It's like a better solution because instead of this, where you say you can jump at this, they say, hey, we can already jump to index 4. Index 4. You don't need to update this array. You don't need this array. You can just say, hey, if you can jump to index 4 and now you can jump to index 5, that's even better. So what you can do is actually this and its farthest jump, farthest you can get is index 1, obviously. Our index is 0. Farthest you can get is now wait. If farthest get is less than I, then return false. So you can't even get to this index. Return false. Otherwise, you want to update farthest get to I plus to farthest guessed or I plus nums at I. And in the end, you can just stitch all this code. Yeah, that looks good too. So it's kind of like that example I was showing you here. Instead of doing this true and then updating them all, you just update, hey, this is the farthest we can get. And if we can get this far, that means we can do any of these indexes. And if we can get this far, we can check any of these indexes and update, and you're good. So yeah, I didn't even get the most optimal solution, but you know, it's fine. Mine was a bit brute forcey, honestly. But again, it's like, it's fine. This was just an optimization you could have made on it. Believe it or not, I've done a similar problem to this, but it was a math problem. Then you could calculate a function to determine what this value is over here. So there's a better way to do it with actually just using basic math. But the idea is you have these x's, right? And what you want to do is you want to find this last x. So let's make it O. And you start here, and you have two decisions. You have one decision to go here, one decision to go here. Here you have two options. Here you only have one decision. So if you're here and you want to get to this block, since you can only move down and right, you only have one decision. So one path, one path, one path, one path, one path. To get to like this x, you only have one path, which is straight down. Because you can only move down and right. If you can move left, there's infinite, right? You just move left, right, left, right, left, right. Here you have one path to get here and two paths to get here, and you can move down to here or you can move right. So that's 3. So that's 1 plus 2. This again is 3, 4, 5, 6, 7, 6, 10, What is this? We'll just do x. 11, which is x1, x2, and x3. Let's do dot, actually. I feel like that takes up less space. No, it doesn't. So there's 13. Is 13 the answer? 28. Why is it 28? Unique paths. Yeah, there's 2 unique paths here, 3 here, 4 here, 5 here, 6 here, 7 here. 10, 15, 21, 28. Okay, I wasn't adding it properly. 10, 15, 21, 28. You see how that works? Because you just add the 2 numbers adjacent to it. So the one above it and the one to the left of it. Now instead of doing like the actual solution, which is just generating a map and then going through the array, what's the function we can find there for this? Because you could just make an n by n array and solve it. What's the function? So we know the top. We know, what do we know? We know first row is equal to 1, and we know the first column is equal to 1. 3 x plus 2, x plus 3, x plus 4, x plus 5, x plus 6, x plus 7. So if we have a variable, the second row is x plus 1, x plus 2, x plus 3, x plus 4, x plus 5, x plus 6, where x is initially 1. Because let's say x is equal to 1. Because that's what we start off at, right? As the first row and first column. Actually, yeah, so x is equal to 1, x plus 1, 2, 3, 4, 5. You missed one space. X is equal to 6, x plus 6. So first row is like that, then x is equal to 1, x plus 2, x plus 3, x plus 2, x plus 2 plus 3, x plus 2 plus 3 plus 4. Is that right? Yeah. So x plus 2 plus 3 is 1, 2, 3, 6, 10, x plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Okay. So I hope you guys see the pattern here. Every time we go down, you just increment by so 6, x plus 2, 3, 4. So 2 plus 3 plus 4, 5, 6. You just add value in the sequence. So it's just 1 really. So let's just ignore this x thing. So 1, this is 1 plus 1. This is 1 plus 2. 1 plus 2, 1 plus 2 plus 3, 1 plus 3, 1 plus whatever. Yeah. Okay. So 1 plus 2, 1 plus 3. So if it's this value that we're looking at, we just need to know how far do we have to add to. So this is 10, 6 plus 7. Yeah. I think I skipped one here, which is plus 5. So this is 10 plus 5, and then there's plus 5 plus 6. Okay, plus 7. Now, what do we know? Is this is 1, 2, 3, 4, 5, 6, 7. 7. But 6, 1 plus 2 plus 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4. I'm trying to find a pattern here. So that'll help us. 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5, 1 plus 6. Yeah. Damn, there's probably something here. I don't know what it is. I don't know what it is. 7 and 3. 7 and... Alright, that's why I'm not a math major. Dang. I swear there's something here. Okay, so this is x plus column number. Now this is x plus, yeah, I don't know what it is, man. I don't know actually. So this is why I gotta practice my quant math. I don't remember how to do this problem. So if I add another one here, 1, 4, now this is 10, this is 20. Yeah, yeah, don't really think of a good solution yet. I'll put this in the back of my mind to think of a math problem or a math solution for this, because there is one. I know it exists. I just kind of forget how to do it. I was trying to find a pattern here, but can't find a good one. Because if you add, actually let's redo this. If you have A, B, A, and A, and you have B, which is A plus A, and you have B here, and you have C here. Actually, this one would be C, and this one would be D. There should be a pattern to this, like 3x3 is equal to D, which is equal to C plus C, which is equal to B, which C plus C, which is equal to B plus A times 2. 2C, which is equal to B plus A, 2 times B plus A, which is equal to 2 times A, 2 times 2 times A, plus A. Oh, damn, now I think we got a good problem, good solution. So, with this following this logic, we get 2A, 4A, 5A. That's what we get, 5A, which is equal to 5. But that's 6. Why is that? Well, let's see. 1, 2, 3, plus 3 is 6. Okay. Is equal to 2C. And each C is B plus A. 6. And each B is, oh no, plus 2A. I gotta carry this over. 2A. Which is equal to 6A, which is correct. So, for 3, what is that? That is 2 times 2 to the power of 2 plus 2 for 3, 3. And then 4, 4, let's see, A, D to plus D. Yeah, let's just add 4 by 3. C, D, E. This is equal to E, which is equal to 2D. Okay, so 2D, which is equal to 2 times 3 times 3, which is equal to 2 times 3 times 3. So it doubles every column you add. Yeah, see it doubles right here. So A AD is E, G. Oh yeah, so every time you add a new one, so 5 by 3 is double. Is 2x. So 3 by 3, 4 by 3 is not 3x though. What do you mean? 3 by 3 is 6. 4 by 3 is 10. 3. But it's made out of 2Ds. 2Ds. This is not D. This is A, B, B and A make C, C and A make D. Oh, dude, using letters is a terrible idea. Okay, yeah, using letters is literally god awful. Because I'm using them wrong. So it's equal to 6. It's equal to 3 plus 3. 2 times 3, which is 2 by 3. Oh, the answer at 2 by 3 doubled. 2 times the answer at 2 by 3. And that's equal to 2 times the answer at... No, it doesn't double there. One plus the answer at 2 by 2. Yeah, I guess I gotta brush up on math because I'm not figuring out the pattern here. Yeah, that's definitely not right. Okay, might as well write the solution now. Because you see the pattern of how it's generated? And by... Damn, I gotta practice math. Okay, for int I is equal to 0. Yeah, actually this is pretty trivial. Yeah, it's pretty easy. But what's the math way to do it? What is the math way? So f of x comma y is equal to f of x minus 1 comma y plus f of y x and y minus 1. That's basically a recursive function that we convert to dynamic programming. Is there a pattern to how these increase? So let's see. Can I zoom into? Yeah, sure. 1, 2, 3, 1, 3, 6, 1, 4, 10, plus 3, plus 6, plus 4, plus 10. Oh, sure. Let's see. In each, try to find a pattern. So you could just use M and N to get a solution. So plus 1, plus 1, plus 1, plus 1, plus 1, plus 2, plus 4. No, plus 2, plus 3, plus 3, plus 6, plus 4, plus 10. Yeah, it kind of builds off the last one, right? So you add 1, which makes sense. But is there like a nice function to define it? I don't know. Oh well. I'll think of it later. Yeah, the coding solution is trivial though. Trivial. The math solution, I don't know about that. That one's kind of interesting. Oh, dude. Oh my god. Okay, I got it. What I have to think about is statistics. Because we have something called choose, which is like n choose r. So right away, when we look at this problem, I was looking for patterns, but if you think about it in a statistics point of view, for these positions, there is... Okay, think about it this way. You have to move... How many moves you have to make? Moves you have to make. Here's a hint, it's always going to be the same. You always have to make 1, 2, 3, 4, 5, 6, 1, 2, which is n minus 1 and plus m minus 1. You got to do 0 to n plus m minus 2 moves. Out of those moves, n minus 1 have to be vertical, so down, and m minus 1 has to be horizontal, so which is right. So the solution is n plus m minus 2, choose n minus 1 or m minus 1, it doesn't really matter. We could do this, so we could do 7 choose 2. Do 2. How many moves do you guys make total? We gotta make 1, 2, 3, 4, 5, 6, 7, 8. 8 choose 2. My bad. 28, which is the correct solution. And if you look at this one, how many moves you have to make for 3 and 2? You gotta make like 4 moves. 4 choose 1. 4. 3. Dude, I swear this works. X, 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 X. 1, 2, 3, 4. Actually, for the last one, you can't really choose. 1, 2, 3. One, two, 1, 2, 1, 2. No, this output is wrong then. You could go right down. Dude, it shouldn't matter. Alright, okay, I'm drawing it wrong. So, you go right, down, down. Oh, 3. My bad. 1, 2, 3. Yeah, okay, so it's 3 choose 3 or 3 choose 1, which should be... No. It's 3 choose 1. 3 choose 1 or 3 choose 2. My bad. Because you can choose... You have 2 moves to go vertically and 1 to go horizontally. Okay. Okay, so that's how you do it the mathy way. I was trying to find a pattern, bro. I forgot about basic statistics. Good stuff. Good stuff. It's good to learn like statistics because if you pull that out during an interview, yo, and you know how to explain how choose works, like you can break it down, why it works, like it's not just some function. Yo, you'll be golden, bro. Golden. Coin change. I'm not doing any of these. I'm just gonna finish dynamic programming. Oh, okay. So this is kind of like the jumping game that we had before. So we have coins 1, 2, 5, and amount 11. And what do we need to return? Fewest number of coins to make that amount. Okay, so we can work backwards from 11 and say the fewest number of coins to make 11 is 1 plus, so func few 11 is equal to 1 plus or the min of 3 values. What are those 3 values? Func few 10 plus 1. Func few, because that's like one of your coins, right? You could just make it 10. Func few 9 plus 1, and func few 11 minus 5, 6 plus 1. So it's one of these 3. Now, you're gonna, it's kind of like that one chart. It's always like some graph that shows you how you break up the dynamic problem. Blah, 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 and blah. So you're gonna have, what is it, 10, 9, and 6? Yeah, I kind of remember this problem, so keep that in mind. Keep that in mind. I'm not cracked, like always. So each one is gonna have 3 branches, and you just want to find the one with the fewest, like depth of the tree. So if you make a tree out of this, it'll be 10 will have branches. I'm not gonna draw the rest of the branches because it's pain. 10 will have branches. 9, because that's 10 minus 1. 8, 5, and you want to find the lowest depth of the tree. Lowest depth of the tree. So where do you use dynamic programming? Store the min number of coins to generate like any value. So this is a top-down approach right here. We could do bottom up. So bottom up is it like the what's the terminology is very like clear. So you want to start from low, the smallest, like the base case basically, up to your example. So what's the base case? The lowest amount of coins to make amount of 0 is you need 0 coins. Then you can go through all your coins and you can say, what is the lowest amount of coins to make 1? And can you even make 1 with the coins that you have? So we can make it because we have 1 in our coin list. But how do we check this? We check, can we make 1 minus 1? Can we make 1 minus 5? Can we make, or 1 minus 2? Can we make 1 minus 5? And these are the coins that we have, 1, 2, 5, right? So this works off our base case. If our base case didn't exist, then we can't make amount 1, right? And then we can always make the next amount because we can make like 1 more coin, 1 more coin, 1 more coin. But you kind of get the idea. And then if you can make an amount, we could just leave it as like amount question mark. We could just leave it as -1 by default. So that means you can't make that amount. And then every time you try to make an amount, you want to take the minimum value of these. So minimum amount, these two are invalid, so these two are invalid. 1 minus 2 is -1, that's invalid. So what's the minimum amount of coins to make 0? Is 0 coins. So you're always going to win. So, and it's 1 plus this. Because you're including previous, you're including the current coin, which is in that 1, 2, 5. So it's kind of just like this, but you're working the other way up. So from 0 to n. And we can make a solution. This is dynamic programming. Few make dp. Fewest can is new int array of amount plus 1 because we want to include 0. Arrays.fill fewest can with -1 and fewest can of 0 is equal to -1. This is our base case. Okay, now what do you want to do? For int I is equal to 1, I is less than amount or less than or equal to amount. I plus plus. And then we want to iterate through all our coins. Seeing coins. Oh shit, I don't know how to do this. How do you do this? How do you do this? Okay, if amount minus coin, if I minus coin is greater than or equal to 0 and fewest can of I minus coins is not equal to -1, I minus C cur coin. So I minus cur coin is greater than or equal to 0 and fewest can of I minus cur coin is not equal to -1, then we can update it. But if fewest can of I is double equal to -1, you should update it. If value is invalid, -1, then always update can make coin. Else you want fewest can of I to be the math.min of whatever it already is. And whatever coin you're currently looking at plus the fewest can of I minus cur coin. Okay, and you just want to return fewest can of amount. Okay, whatever. What is this? Oh, output should be 11, yeah? Oh, it's equal to 0. Submit. Alright, sure. Good enough for me. Last question, and then I can do like some very, what would I call it? I gotta do company specific questions, but it's like they sent me the question beforehand. They're like, it's gonna be something based off this, so lucky me. Lucky me. I would prefer if it was just a random interview, because now it feels like I got prep for that specific question. Okay. Just text me. So we want longest increasing subsequence. Okay, longest increasing subsequence. Strictly increasing subsequence. Ah, shit. Okay, what is a longest? So we need to do dynamic programming. Okay, solution could be, how many values does this have that are smaller than this? I kind of remember this. And 1. So 10 has one value that's smaller than it. 9 has, well, it's not smaller than it than itself. So the longest increasing subsequence is actually our DP array. So for 10, there's nothing behind it. For 9, you look at 10, but 10 is greater than 9, so you don't update it. For 2, you look at 10 larger, 9 larger, keep it the same. For 5, 10 larger, 9 larger, 2 is smaller, so you update it to whatever 2 is plus 1. 3, 2 is plus 1, because 2 is smaller, you can update it. 7, it's larger than both 3 and 5, so you can update it to 3. 101 is larger than 7, and 18 is also larger than 7, so 4. But yeah, that's how you do this problem. I do remember it. If I could break it down for you guys. So in each step, you can work with it backwards. You think, how many values are larger than 18? So you look at all the values that are beneath it in the rest of the array, and you get to these are like multiple graphs in my opinion. What do you get? You get 7, 3, 5. Let's just make an array. You get to 7, 3, and 5, right? 18 has 7, 3, and 5 smaller than it. Now, for each of these, you say, hey, what does 7 have that's smaller than it? Which is also behind it. So you want to take the max of whatever our function call is. So func get small, whatever small it is, whatever smaller than 18 that's also behind it, and behind. So get small and behind of 18. So you want to do the max of whatever these 3 values are plus 1, because we're including 18. And then this is kind of like a recursive function, but then you want to do this for all values. So what you want to do, get small and behind of 101. That's 1 plus get small and behind like all of these values, like 10, get small and behind of 9, so on and so forth. Let's do 2 and behind of 2, get small and behind of 5, But what you see is you're going to be recalculating values. This whole process recalculates values. And that's not good. So we had to add some memoization, which is either like a hash map of get small and behind like the index, and the get small and behind values, like how many values of it are smaller and behind it. So what's the longest sequence at that value? So get small and behind is equal to longest subsequence that ends at this value. Okay, so then you could have this hash map and solve it, or you can get a bottom up approach, which is instead of starting at the last value, let's start at the first and work up to the last. That's kind of the explanation I showed over here. Okay, yeah, bottom up is usually my favorite because it's very, very clean. But I think it's good to practice top down as well, just so you like understand both ways of doing it. Should I do top down right now? Nah, I don't want to. But you guys should understand it. It's pretty simple. Like it's always like a recursive function with the hash map, or some other form of recursion. So if you're doing it iteratively, you always like use a stack or a queue or something. But you just have a hash map and you just continue this process. And you save values that you pre-calculate, and that's memoization. Okay, I think that's all the Leetcode problems from the medium playlist I'd want to do. These ones are kind of lengthy. They're good problems though. I think you should do this if you have time. I don't really want to do it. Backtracking is not that useful. Arrays, linked lists, trees, dynamic programming. Maybe some design. I don't think math is that useful, but it's kind of cool too. Like there's like cool things you can learn when you're doing this. But yeah, that's it. Okay. Bye. Stream over.